All right, let's dive in. Today, we're talking about the unsung hero of our digital world, the secret engine that makes everything you do online both incredibly fast and incredibly private. It's happening right now, and you probably don't even notice it.
Have you ever stopped to wonder about the speed of online security? I mean, we're constantly sending information back and forth, and it's all being protected in, the blink of an eye. It really sets up a pretty fascinating mystery.
Just think about what you've probably already done today. Maybe you sent a message on a secure app, bought something online, logged into your email. All of these things we just do, and they're all wrapped in this invisible layer of protection.
And we're not talking about a little bit of text here. We're talking about huge amounts of data, high-res photos, entire video streams, massive files. All of it is being locked down on the spot millions of times a second all over the globe. So that's the big question, right? How on earth is this possible? How can we perform this massive global-scale encryption with such mind-boggling speed and efficiency? It really does feel like some kind of magic. But it's not magic, it's just some seriously brilliant engineering.
Well, the answer to that mystery is modern symmetric cryptography. And this isn't just another tool in the box. You can think of it as the heavy-lifting workhorse of the digital security world. It was designed from the ground up to do this one job: protect huge amounts of data at high speed.
So what exactly is it? Well, at its core, the idea is actually super simple. It's a system where two people agree on one single shared secret key. That's it. That one key does all the work. It locks the data, and it's the only thing that can unlock it. Simple, elegant, and really, really effective. So let's break that down. The key characteristics are right there. Number one, there's only one shared secret key. Number two, you use that exact same key to both lock and unlock the information. And number three, and this is the most important part for our mystery, the entire system is built for one thing above all else: pure, raw speed.
And this sentence just hits the nail on the head. If you need to protect a ton of data without slowing everything down to a crawl, this is what you use. It's literally the reason you can securely stream a 4K movie without endless buffering.
But why? Why is it so incredibly fast? To get that, we need to see what makes modern ciphers so different from the old-school ones. The secret isn't just about using fancier math, it's a fundamental change in what's actually being encrypted.
See, classical ciphers, things like the Caesar cipher from ancient Rome, they worked by messing with letters of the alphabet. But modern ciphers, they don't see letters at all. They see the raw data, the ones and zeros, the bits that make up everything on a computer. And guess what computers are absolutely amazing at? Processing bits at unbelievable speeds. That's the key to their efficiency.
Now, inside modern symmetric crypto, you basically got two main flavors. The first is what we call a block cipher. The easiest way to think about this is like an assembly line. It takes a standardized chunk, or block, of your data, encrypts it, and then grabs the next one, block by block by block.
And the other flavor is the stream cipher. So instead of waiting to fill up a whole block, this one encrypts your data as it comes in, literally one bit at a time. It's like a continuous flowing river of encryption. This is perfect for things that happen in real time, like a video conference or a secure phone call.
Okay, so this all sounds perfect, right? It's fast, it's efficient, but there's a catch. A really big one, actually. A kind of paradox that creates a major problem.
And this statement just sums up that dilemma perfectly. That single shared key is what makes it so fast, but it also creates this huge logistical nightmare.
Yeah, think about it. If you and I need the same secret key to talk securely, how do I get that key to you? I can't just email it to you or send it in a text because the whole internet is insecure to start with. Anyone could grab it. So how do you share the secret before you have a secure way to share things?
And the solution is it's so clever. Symmetric cryptography doesn't solve this problem by itself. It calls in a partner for help, asymmetric cryptography. It uses this other, much slower type of encryption for one tiny but absolutely critical job, just to share the secret key safely.
So we know it's fast, and we know how it cleverly gets its key. But the other big question is, how do we know it's actually secure? What gives us the confidence to trust these algorithms with our most private information? Well, our trust really comes from three main things. First, these algorithms are built on really solid, well-understood mathematical foundations. Second, they're intentionally designed to stand up against all the known ways attackers try to break codes. But this last one is the most important. They aren't secret. The designs are published for the whole world to see, for every expert cryptographer to analyze, attack, and try to find a flaw. Their strength comes from surviving that constant public challenge.
All right, let's zoom out for a second and put all these pieces together. Let's see how this whole process works in the real world when you make a secure connection.
Think of it as a handshake. Step 1. The slow but super secure asymmetric crypto is used for one job and one job only, to safely agree on a temporary shared secret key for this one conversation. Step 2. Once that key is in place, the fast and efficient symmetric crypto takes over and does all the heavy lifting, encrypting all the actual data. The result? You get the best of both worlds, rock-solid security and incredible speed.
Now, I gotta point out, this has been the 10,000-foot view, right? We've stayed at the level of what it is and why it works. We didn't dive way down into the deep, heavy math behind specific algorithms like AES or DES or how key schedules work. That's a whole other rabbit hole.
So, we've solved the mystery of how our digital world can be both incredibly fast and secure. It's this beautiful teamwork between two different kinds of cryptography. But this leaves us with one last, really interesting question. Now that we know how it's done, which was the pioneering algorithm that first set this modern standard and really changed the game for everyone? We'll dig into that story next.